Here I'm going to start with a modeling of the main point of this e-learning module, which is the highly mobile nature of valence electrons. And so before I even read the objective for this e-learning module and then establish an assessment boundary for this module, I'm going to demonstrate or model for learners the fundamental nature of the sea of electrons, or metallic bonding, which is these highly mobile electrons. And so I have two different animations on the screen to start that highlight the fact that metal cations are fairly static. They don't move very much at all. But the electrons within the sample of metal are highly mobile. So I start with a modeling of that using GIFs. At the end of this module, you should be able to describe the electron sea model for metallic bonding and explain why metals are good electrical and thermal conductors. In this module, we will not consider other general properties of metals such as luster, malleability, and ductility. Instead, we will focus on conductivity. I chose to focus only on these particular aspects of metallic bonding because they're much easier to visually model, because the focus here is the highly mobile nature of the valence electrons. Other aspects of metals and metallic bonding also involve these highly mobile electrons, but they become a little bit more convoluted, a little bit more nuanced. These are the two basic concepts behind metallic bonding, and so I chose to only focus on these as opposed to all of the different characteristics of metallic bonding. In previous sections, we discussed chemical bonds in ionic compounds and covalent compounds. Metals are held together by a different type of bond, resulting in some of the unique properties of metals. Solid ionic compounds cannot conduct electricity. The electrons in an ionic crystal lattice are tightly bound to the atoms that make up the lattice. If the ionic compound melts, which destroys the crystal structure, or if it is dissolved in water, then the ions can conduct electricity. The valence electrons in a molecular covalent bond are also locked inside bonds, making molecular compounds poor conductors. So before we go on to the check for understanding, I've delineated why metals, which use metallic bonding, are good conductors of heat and electricity, but why or when ionic compounds are not. One property shared by all metals is their ability to conduct electricity. A metal contains valence electrons that are mobile and able to move throughout the metal, and they are much better conductors than molten ionic compounds. Let's take a moment to check your understanding. Under what conditions can an ionic compound conduct electricity? And so here we have a couple of options, and we do have to select all of the correct options here. Under what conditions can an ionic compound conduct electricity? There are two conditions. One, if it is dissolved in water, and the other is if it is melted and it enters the liquid state, also known as the molten state. And so once I hit submit and I have all of the correct answers selected, I can click the green box and I can move on after a small delay to let the learner get ready for the next piece of information. Metal electrons move freely in empty, overlapping orbitals. The outermost energy level of most metal atoms contains very few electrons. The S-block metals contain only one or two valence electrons. The highest p sublevel, which can hold up to 6 electrons, is empty. The D-block metals contain an empty p sublevel in their outermost energy level, and often empty d orbitals in their next lowest energy level. This is review from a previous chapter, but what it is bringing back to the learner's mind, entering into that piece of working memory, is that there are very few valence electrons available in a metal. Relative to that small number of valence electrons, there are a large number of vacant orbitals. And because these are bonding atoms, those vacant orbitals overlap. And so again, that's the next piece of describing the sea of electrons. And again, I have a different animation on the screen modeling how the metal cations themselves stay relatively still while the surrounding electrons are highly mobile and delocalized. But here, in this portion, this is where I introduce those particular terms. Within a metal, the empty orbitals in the outer energy levels overlap. This overlapping of orbitals allows the outer electrons of metal atoms to move freely throughout the entire metal. The electrons do not belong to any specific atom, so they are called delocalized electrons. These delocalized electrons in a metal form a sea of electrons around the metal's atoms. The atoms are packed together in a crystal lattice, similar to an ionic crystal lattice. The attraction between the metal atoms and the surrounding sea of electrons is called metallic bonding. Let's take a moment to check your understanding. What is metallic bonding? And so we have another multiple choice question here. There's only one correct answer, and this is a basic definition of metallic bonding that we saw on the previous slide. There are two options that insinuate that there's a repulsion within the bond. That's incorrect. Bonding is an attraction. And if you did not take away that the bonding, the attraction, is between metal atoms themselves and the surrounding sea of electrons, and you were to choose the incorrect answer, you would actually have to go backwards and go through that section again. Metal electrons move freely in empty, overlapping orbitals. The outermost energy level of most metal... But once we move through and we get... Let's take a moment to check your understanding. Answer correct. What is metallic bonding? We can move forward after we choose the correct answer. Again, there's a slight pause so that
the outer electrons in metals are able to move a lot more freely than electrons in nonmetals and metalloids. Partially empty energy levels offer multiple positions for any given electron. Since outer energy levels of adjacent atoms are relatively close together, electrons in metals can also move from one atom to another. The result is metallic bonding.
I chose to include this and one more embedded video that I did not make. I'm using from another source, but I chose to use this because it is so effective at visually modeling the nature of the sea of electrons that I cannot recreate this modeling in any other way. Students do not get this visual in the lab. They do not get this visual in the textbook. They can't get this visual from a lecture. But seeing these animations allows them to have a visual concept of what's happening within the metallic bond so that they can have some sort of foundation to attach the definition of the sea of electrons to in their mind.
The positive metal ions remain in relatively fixed positions, while the negative electrons are free to move about. This creates bonds extending through the metal in all directions and leads to many of the observed properties of metals.
Let's take a moment to check your understanding. Which is most likely the better conductor of electricity? A block of solid sodium or a sodium chloride crystal? This question happens to be a little bit more difficult because I'm asking the learner to differentiate between something that is only a metal and something that is ionic in nature. And so we see the solid sodium. The word solid, obviously it indicates that it's in the solid state, but it also indicates that the only element present is sodium. And so it's only the metal sodium, as opposed to option B, which is sodium chloride, the chloride anion being non-metallic. And so once we click the correct answer, which is E here, we can click the green button to move on to the next portion. Chemical bonding is different in metals than it is in ionic, molecular, or covalent network compounds. The unique characteristics of metallic bonding gives metals their characteristic properties, which include, but are not limited to, electrical and thermal conductivity. Before I move on with the rest of this slide, I wanted to point out that I have no idea why the background of this particular slide would not match the background of the other slides that I made. I do not know. I spent quite a bit of time trying to figure out why it was not formatting how I wanted it to. I could not figure it out. But notwithstanding the format, the purpose of this slide is to give, again, a visual model for the electron clouds of elements in different types of bonding. So we have metallic bonding on the left, which is what we're covering right now, but we also have ionic bonding and covalent bonding modeled here, even though we covered them in previous sections. And what this allows students to do is compare and contrast how the electron clouds of different elements look, or how they interact in different types of bonding. And so over here we see the fact that these different orbitals overlap in the metallic bond, and in this entire mass of blue on the screen here, electrons have free reign. They can move anywhere in the entire sample. Compared to ionic bonds, which is a completely separated pair of ions, but it's the positive versus negative nature of those ions that actually causes the attraction. There's no overlap of electron clouds. It's simply the positive charge and the negative charge attracting one another, which does have some similarities with metallic bonding. It's the positive nature of the metal cation and the negative nature of this sea of surrounding electrons that causes the attraction. But in ionic bonding, there's no overlap of orbitals. But when you talk about covalent bonding, there is an overlap of orbitals, as is demonstrated by the fact that these blue clouds, in fact, overlap. But there's no overall charge differential. There's no positive versus negative charge of different ions, and the electrons don't move through a huge mass of elements. They just are able to move within the single molecule that's covalently bonded. Electrical conductivity is when the sea of electrons in a metal allows electric current to flow freely. This makes metals good electrical conductors. Metallic bonding also causes metals to have other characteristic properties like thermal conductivity, in which the sea of electrons can transfer heat as well as carry electrical current. Therefore, metals are both good thermal conductors as well as electrical conductors. Let's take a moment to check your understanding. What specific property of metals accounts for their unusual electric conductivity? So at this point, the learning module has hit hard that it's the highly mobile nature of electrons that allows the concept of metallic bonding to actually work, the sea of electrons. And so we have two possible correct answers, A and C. It turns out that it is a bond, so it's going to be within the bonding network, not outside of it. And that would be like some sort of intermolecular force. So once we get the answer correct, we can click the green button. And with our few second pause so that the student can be ready to go into the next concept or video in this case, we take a pause.
Heating a material adds energy to it. As energy is added, the electrons move more quickly from low energy orbitals to high energy orbitals. By doing this, they also move through the material. In metals, the electrons are so loosely held that this movement happens easily. Heat conducts quickly through the metal.
Again, this embedded video is not something that I made, but I really, really like these videos because, again, they model the movement of delocalized electrons while establishing that the positively charged metal cations are relatively stationary. They do have some vibration, that's true, but they're relatively stationary. And then we'll move from the concept of thermal conductivity, which is simply the higher speed movement of the electrons and maybe the more violent vibration of the metal cations. But again, in this particular module, we're focusing on the mobile nature of the electrons, not kinetic molecular theory that would talk about the vibrations of the cations. This models movement of electrons. And in the next portion of this video, there's a modeling of, again, the movement of electrons, but in this next case, it's going to be as a result of the application of an electric current.
Metals also readily conduct electricity. A potential difference applied to a piece of metal attracts electrons from the negative end to the positive end. Because the electrons in metals can move freely from orbital to orbital, electricity flows freely through the material.
Let's take a moment to check your understanding. What properties of metals contribute to their tendency to form metallic bonds? And this will be the last thing we do in this module. We see that all three of these options are in fact correct. Not because it's new information. In fact, this is actually old information from the previous chapter. What's new about this particular module is that we are using old information, in this case, sparsely populated outermost orbitals, low ionization energies, and low electronegativities. We are using those old pieces of content to predict the function or nature of metals as they bond to each other. So, with one last submit, I can move on, and I can be at the end of my learning module.